okay and the connection is all right. It's a great pleasure to talk to you. It's a little bit disarming not to be able to also see you, but we'll see how this goes. It's probably something we need to all get very used to. So look, as I've said, I'm Australian. I live in Australia. I'm at Monash University, which is in Melbourne. And I'll talk a little bit about some of the things we're doing in aluminium alloys. But before getting into the technical content, I think I'll just give you a little bit of a background of where I come from, what my university's like, and these sorts of things, because we're a long way away, and maybe some people don't know of Monash. So Monash University, it's quite a big university. It's a comprehensive university in the spirit of the North American universities, where you have many different faculties. And so we have 10 faculties, everything from medicine, arts, etc., all the way through to engineering. And actually, even though we're an Australian university, we have campuses in 5 different countries. And the main ones are in Melbourne. And so you can see here, here's Australia. And so Melbourne is right down the bottom here. And, you know, what we've got here is Indonesia, Papua New Guinea, Vietnam, Laos, Thailand, Malaysia, etc. So we're in this part of the world. We have a full-blown campus in Kuala Lumpur, but our main campuses are in Melbourne. And Melbourne is on a bay. It's on the water just here. And this is the city centre, the central business district of Melbourne. We have a campus very close to the city centre, which is a campus that focuses on pharmacy and pharmaceutical development, which is pretty important at the moment. And then our 2 main campuses are Caulfield and Clayton. And Clayton is the largest campus. We're about 15 kilometres out of the centre of Melbourne. And this is where the engineering faculty is located and where I'm housed. And so I said Monash is quite a large university. We have nearly 80,000 students and about 18,000 staff. So at least it's the biggest university in Australia, and at least by Australian standards, we consider this to be pretty large. So I was saying, so Monash University is located in Melbourne. That's where I call home. And the main campus of Monash University is this one here, Clayton. It's about 15 kilometres. So about 10 miles out of the centre of Melbourne. And Melbourne, if you ever get the opportunity, is really spectacular place to live. And so for any of you who do make your way down to Australia on holidays, please feel free to reach out, and I'll be very happy to show you around Monash, but also for you to enjoy Melbourne, which is really a wonderful place to live. And that's something that's really kept me in Australia and at Monash University. So the engineering school at Monash is a rather classic one. We have 5 engineering departments. And as was said at the beginning, I'm in the material science and engineering department. But we are in a technology precinct. And so right next to Monash, Clayton, is the Australian synchrotron, which is quite handy, and our national laboratories. And so this creates a very nice materials and technological precinct in Clayton. And so within the engineering school, I'm part of the metallurgy and corrosion cluster. And so we have a good critical size group working on problems associated with metallurgy. Some of these names will be very familiar. Michael Cruz has just joined us from Manchester, and he's currently in quarantine in Australia. He's just arrived. Jin Feng Ni, who's an expert in magnesium alloys that some of you might know. And this might be a name that's familiar to some of your more experienced colleagues. Chris Davies is actually the head of our mechanical and aerospace department, but he did his bachelor's and his PhD at Imperial. We have some researchers working in powder processing, microscopy, and we have a pretty active corrosion and electrochemistry group. And so we work on most classes of engineering alloys, and probably to give you a feeling for the size of this cluster, this consists of probably about 70 PhD students in total and about 35 to 40 research fellows. So it's quite an active group in metallurgy. In my own group, I tend to work, most of my activities are on steels and aluminium alloys. So probably half of my work is on steels. Probably about 30% of my work is on aluminium alloys, and especially the precipitate strengthened aluminium alloys that I'll talk a little bit about today. And then I do some work on copper and brasses. I split my time pretty equally between microstructural evolution, whether it be recovery and recrystallization or other forms of phase transformations, and mechanical properties. And I'm particularly interested in strain hardening behaviour, and over the last couple of years have become more and more interested in fatigue and wear, and I'll talk a little bit about fatigue today. And so I keep a reasonably small group, actually. So at any one time, I would have roughly between 5 or 10 PhD students and 2 to 4 postdocs. So that sort of gives you a little bit of a snapshot of Monash, Melbourne, and our metallurgy and corrosion cluster and my research group. And what I'm going to do today is really talk about this problem here, coupling of plasticity and precipitation, and I'm going to link it to some interesting problems in fatigue. And I'm going to do this in the context of precipitate strengthened aluminium alloys, and so especially the 2000, 6000 and 7000 series alloys. So this work, of course, it's a big group of people that work together to do this research. But what I'm going to talk about is really the work of 2 young ladies, Wenwen Sun, who was a former PhD student of mine, who then did a postdoc, and she's currently a professor at Southeast University now in Nanjing, and Qi Zhang, who has just completed her PhD and just gone back to work in industry in China. And so these are the 2 who did the bulk of the work that I'll present. But I'm going to talk about dynamic precipitation in the context of aluminium alloys, and maybe some little bit different takes on this phenomena. So I think, you know, these are sorts of plots that we will all remember from second year undergraduate when we first started to learn about phase transformations. And we're used to knowing that any sort of phase transformation that let's say phase transformation that has a change in chemistry, that as we change the temperature, we see a C-type behavior, and that's sort of shown here. This C-type behavior where the transformation rate will pass through a maximum at some intermediate temperature. And this is absolutely true for precipitation processes that occur in aluminium alloys. And this is technologically very important. And this C-type behavior guides the temperatures that we choose to do our precipitation heat treatments in commercial aluminium alloys. And so aluminium alloys like aluminium copper magnesium or aluminium magnesium silicon, they are traditionally given a heat treatment at somewhere between 150 or 200 degrees for probably between 6 or 7 or 8 hours up to 20 hours to develop the precipitate structures that give us the interesting properties. And this is all well known, and we've been doing this for 80 or 90 years now. But it's useful to remember, you know, what underlies this C-curve behavior. You know, this is a competition between thermodynamics and kinetics, and it leads to us choosing an intermediate temperature for our heat treatments of precipitate hardened aluminium alloys. And we do that so that we can make a reasonably fine distribution of particles, but we don't have to wait forever for that to happen. And that's quite important because from a mechanical properties point of view, usually what we're trying to do is make a very nice fine distribution of particles, fine and uniform. And that means we want lots of nucleation and a little bit of growth. Now, the problem with nucleation is we want to have a large driving force, which means we want to go to lower temperatures. And here this is written in the context of a fluctuation type model for the nucleation process. But even if you don't believe in that, in aluminium alloys, you know, whatever the mechanism of nucleation is, certainly we need a thermodynamic driving force. But the problem is that in aluminium alloys, these particles have a chemistry that's different to the bulk, so diffusion is also required. And it's that competition between thermodynamic driving force and kinetics that gives this C-type behaviour. Now, there's two things to take from this, well-known picture that we learn as second-year undergraduate students. The first is the temperatures that we use to do precipitation treatments in something like aluminium, they are a compromise. It's a compromise between thermodynamics and kinetics. Actually, what we would like to do is maximise the nucleation and have very little growth to get this really nice, fine and uniform distribution of particles. But to maximise nucleation in a thermodynamic sense, we want to go to low temperature. But at low temperature, we don't have enough mobility. And so we make a compromise. The second important point I want to make is that the intermediate temperatures that we choose that give the maximums in the transformation rates are very similar for both nucleation and growth. And what this means is that it forms a constraint on the combinations, or let's say the competition between nucleation and growth, and that provides a constraint around the combinations of particle number and size that we can achieve experimentally. And so that has an influence on the types of mechanical properties we can develop. So this compromise in choosing conditions for precipitation all comes about because we use a single state variable to control both mobility and driving force. We use the temperature. And so we started looking at this problem and say, well, what if you don't have to use temperature? What if you can create mobility in a different way and try to decouple, partially at least, the thermodynamics and the kinetics to try and control precipitation? And so certainly you can. And we know that there are different ways to create mobility in materials. In the sorts of materials that we're interested in, the mobility occurs by a vacancy exchange. And so any sort of process that we can use to inject vacancies into the material can give some mobility independent, or let's say partially independent, of the temperature effect. So irradiation is one way. And so certainly this is well known for people working in the nuclear industry. You can create point defects by irradiation, and those point defects can mediate mass transfer. And that's interesting, but it's perhaps not so easy to apply, and often we want to avoid this, in fact. But another very interesting way to give some mobility to materials is actually use plasticity. Now, in FCC materials like aluminium, our dislocations contain a certain concentration of thermal jogs. And when the dislocations move through the material, the dragging of those jogs leads to the generation, it's a purely geometric effect, the generation of vacancies. And so plasticity generates vacancy, actually then generates interstitials as well. But in this case, we're particularly interested in the generation of vacancies. And that dragging of jogs to create vacancies can lead to the development of a non-equilibrium vacancy concentration. And these vacancies can be used to mediate mass transfer. And so we have some models to try and describe this vacancy generation approach. And one of them is shown down here. And it's a very, very simple idea. Really what we're talking about is we're using a fraction of the work done to create vacancies. So dC dt is simply equal to the stress times the strain rate divided by the vacancy formation energy. And it's a very simple idea that you're using a fraction of the mechanical work to create vacancies. And so the fact that we can use plasticity to drive mass transfer or diffusion, this is actually already well known. And so we've done lots of this sort of work in the past of looking at the coupling of plasticity and precipitation, and in particular the generation of vacancies, let's say strain-induced vacancies, to accelerate precipitation. And so this is an example in a 7000 series aluminium alloy. So this is an aluminium zinc magnesium based alloy, especially used in aerospace. And this was an experiment where we performed in situ small angle X-ray scattering at a synchrotron at elevated temperature and strained the material at the same time. And we wanted to examine the effect of that plasticity on the growth rate of the precipitates. And so the interesting things here is to look down here at the radius. So this is the radius comparing deformed and undeformed particles as a function of time. And the blue is during straining and the red is without straining. So it's clear we have a very obvious acceleration of the precipitation process, in this case, the precipitate growth process during the plasticity. And as it turns out, quantitatively, we can understand that acceleration in terms of the effect of strain-induced vacancies. And of course, there's many different modes of coupling between plasticity and precipitation, and they all have different signatures in terms of their strain rate, etc. Dependence. In this case, we're able to rationalise it pretty well using strain-induced vacancies. Now, this is in monotonic deformation, and it's at elevated temperatures as well, actually. And monotonic deformation is interesting, but of course we can only apply it so much. Another interesting opportunity is to use cyclic deformation, and cyclic deformation is interesting because you can apply the plasticity without a macroscopic and final shape change to your material. And so this is an example of applying, again, a 7000 series, 7050 in this case, aluminium, zinc, magnesium, copper alloy, where we have applied cyclic plasticity at room temperature under a particular type of loading. It's constant plastic strain amplitude. And so in this case, we're making the dislocations go back and forth in the material, but we're controlling the amplitude of that back and forth motion of the dislocations. And what I'm showing here is the average peak stress as a function of the number of cycles of deformation. And I've got three different states. The green one, this is the peak age state. It already has a very well-developed precipitate state. Almost all the solute has been taken out of solid solution and made into precipitates. And that is pretty stable cycling. The stress is pretty stable as a function of the number of cycles. But the blue and the red curves, these are underaged materials. So they're 10-minute or 30-minute aging at the normal aging temperature for these alloys. And what that means is we have precipitates present, but we also still have some solute remaining in solid solution. And what you can see here is during the cycling, we have this very pronounced cyclic hardening. And actually this cyclic hardening, we've studied this we've characterized this by small angle X-ray scattering, and this is due to dynamic precipitation. The solute that was in solution is being precipitated out. It's at room temperature due to this injection of vacancies from the from the motion of the dislocations. And you see a very interesting thing. The very underaged material, even at room temperature, can be increased in strength to at least as strong as the T6 state. And so we did this work a long time ago, but it raised the question for me that can we use dynamic precipitation at room temperature as a new form of processing? Do we really need to do elevated temperature treatments for aluminium alloys? And it's quite important because these alloys, when we do these heat treatments, I told you before, sort of 150 to 200 degrees is the temperature, but a typical heat treatment would be 10 hours. And so these are very energy intensive processes, and then therefore there's lots of constraints around this. So that led us to thinking about, can we use cyclic plasticity to drive room temperature decomposition of solid solutions and get properties that are interesting? Certainly we know we can drive the solid solution decomposition, but do you get anything interesting from it? And so we've tested this on a whole range of model aluminium alloys, but also commercial alloys. And I'll show you, here, these are 3 commercial alloys. 2024, it's an aluminium copper magnesium alloy, 7075 aluminium zinc magnesium alloy, and 6061. And these are probably the 3 most common aluminium alloys that are used. And so we've taken these commercial materials, we've solution treated them at elevated temperature and then quenched. And so they start as a full solid solution material. And then for each of them, we've designed a particular cyclic profile. And so this profile is designed in a very particular way to control the dislocation motion during cyclic plasticity. We want to drive dislocations back and forth so that they can generate vacancies, but we're not trying to strain harden the material. In fact, we're trying to minimize the amount of dislocation accumulation by traditional forest hardening. We just want to move the dislocations back and forth. And so the way we control this is by controlling the plastic strain amplitude, and we try and keep that down around 5 × 10⁻⁵ or 1 × 10⁻⁴. Now, during the process, the material strengthens because we have this decomposition of the solid solution, and that's why we design a stress profile that increases. So this stress profile is really designed to control the plastic strain amplitude during cycling. And we would typically do this something like 500 cycles. And if you do it at 1 Hertz, that means less than 10 minutes. If you do it at 0.2 Hertz, it's about 40 minutes. And so these are very, very short times compared to the traditional treatment time used for the elevated temperature aging of precipitate hardened aluminium alloys. So I'll show you I'll just show you one example so I can get into then some more interesting new stuff. This is for the 2024, it's an aluminium copper magnesium alloy. And what I'm showing you here is 3 stress strain curves that we would have from the traditional material. The blue is the water quenched. So that is the stress strain curve from the material in the solution treated and quenched state, all of the solute left in solid solution. And the red curve is the peak aged state. So this is the T6 state. It's been given the heat treatment at elevated temperature that allows it to have the highest strength. You can see a UTS here of about 500, a yield strength of about 380. And then the grey curve is an underaged alloy. So underaged, this is treated for times less than the peak age state. So it will have some precipitates present, but also a lot of solute left in solid solution. If we plot the yield strength and the uniform elongation from these 3 curves, we have this completely normal inverse correlation that we typically see in engineering alloys. So here's the peak age state, the water quenched and the underaged. And so the multiple points just correspond to multiple tests so you can see the reproducibility. So if we take a water quenched material and now subject it to the sort of cyclic plasticity that I was just referring to, and remember the idea here is to inject vacancies into the material to drive mass transfer, which can occur at room temperature in aluminium alloys, and try then to be having a decomposition of the solid solution. If I apply this sort of profile and I do that for 500 cycles, then I take the sample off and I do a tensile test, this is what I get. And so it's quite remarkable. This is the black curve, CS we've referred to as cyclically strengthened. That is the stress strain curve from a water quenched sample that has been cycled for about 500 times at room temperature, and we can see we end up with a yield strength that's at least as strong or even higher than the peak age state and a better uniform elongation, and we can see it here. And so what this shows us, and it's not a surprise that we can have dynamic precipitation in something like aluminium, but it's a surprise that the properties can be, the tensile properties can be so good that can exceed those of the peak age T6 state. And that's pretty interesting. It tells us that, well, if you could develop a way to apply such cyclic plasticity industrially, then actually maybe you don't need to apply elevated temperature thermal treatments to aluminium alloys at all. And so some companies are pursuing this using ultrasonics, high energy ultrasonics, and we're working with some of them in this area, and it seems that it will indeed work. And so it's a very interesting thing. Now, if we look at these sorts of microstructures, you know, what's really happening in the microstructure? You can see here some TEM micrographs. Now, these are taken with low angle annular dark. These are low angle annular dark field images. And what we've got is for the 7075, the 6061 and the 2024, we've got 2 images each. So if we look at the 7075, this first image up here, this is the traditional precipitate microstructure in the peak age state. So actually these are all eta prime particles, a very high number density of them. This is the 6061. In this case, you're looking down the 001 zone axis, so you can see the rods in 2 directions. This is the beta prime phase. And in 2024, again, this is down the 001 zone axis, and that very fine distribution there is a very fine distribution of S phase, Al2CuMg. And so these are our traditional peak-aged microstructures, showing precipitates that result from elevated temperature thermal treatments. And it's good to see them because you can see the length scale of the microstructure. The microstructures at the bottom, these are the microstructures of our cyclically strengthened materials. Now, it's important, these 2 microstructures have basically the same yield strength, but the microstructures are completely different. And so the microstructures down the bottom, you can see dislocation loops, and these dislocation loops form as a result of the condensation of the vacancies that are generated by the cyclic plasticity. We see some dislocations, but it's not a huge dislocation density, and that's quite important for us. The second thing is you can see, well, these dislocations, they will give, even the loops, will give a forest contribution to the strength. But the spacing of these sorts of obstacles, they're at least an order of magnitude or 2 larger than the spacing of the precipitates that appear in the normally thermally treated materials. And so these dislocation debris, they cannot be the full story of what controls the strength of these materials. In fact, you need to go in and look at much finer detail at the underlying microstructure. And actually, if you look at it in high-angle annular dark field imaging, you can see a very fine distribution of objects, sort of 2 to 3 nanometers in size. And in fact, we needed to go to atom probe to see it very clearly. And what you see here are 2 atom probe reconstructions. This is from 2024. And this sample here is showing clusters that have formed in the cyclically strengthened material. And the one on the right are the clusters that have formed in the head of exactly the same sample. So we have a sample that we apply the cyclic vibrations, the cyclic plasticity in uniaxially in a fatigue machine. And so this collection comes from the gauge and this collection comes from the head. And it's quite important to do that direct comparison because then both samples have identical thermal histories. And you can see there's an enormous difference in the density of clusters that have formed. And actually, by using some reasonable calculations of what we think is the strength of these clusters as shearing entities, we can rationalize pretty well the increase in strength. So these are really a cluster strengthened material. So this has come about from the coupling of plasticity and precipitation. And there's a number of what we find to be very interesting points about that. By using plasticity to inject vacancies, we're able to partially decouple the thermodynamics and kinetics. Previously, using traditional thermal treatments, we use temperature to control both the thermodynamics and kinetics, and that has some constraints around it. Now, by injecting the vacancies using plasticity, we can partially decouple that. Now, I say partially because, of course, mass transfer depends not only on the presence of the vacancies. Our solute atoms also have to be able to jump into the neighbouring site, and that depends on temperature. So it's only a partial decoupling, but it's a very important decoupling because it allows us to reset a little bit the competition between nucleation and growth. We're able to get a very large amount of nucleation and minimise the amount of growth, and this has some very interesting effects. There is a second effect, and of course, when we're driving dislocations back and forth in our material, we're not only just injecting vacancies. The dislocations can also shear particles. And actually this particle shearing, the competition between the growth of the particles driven by an excess vacancy content and the shearing by the dislocations. In fact, that leads to a steady state particle size, and this can be derived pretty easily, and it agrees very well with our small angle X-ray scattering observations and our atom probe observations, and you end up with objects about 2 nanometers in size, and they're equiaxed. And they're equiaxed because the probability of a dislocation intersecting a particle scales with a particle size. And so in a material that, let's say like aluminium, that's FCC, that has a very nice number of slip systems, then this will lead to equiaxed particles. That's quite different from what we see experimentally. Perhaps the most interesting thing for me, and the reason I got really involved in this in the first place, is that by using dynamic precipitation and controlling the plasticity, we can spatially homogenize the precipitation process. Now, think about this. Dislocations move in our microstructure wherever it's most easy for them to move. And that is where they will generate vacancies. And if there's solute available, then they will drive dynamic precipitation, which will strengthen that region. So generating a microstructure in this way using plasticity, it is self-regulating in both space and time, and so it leads to extremely uniform microstructures. And indeed, the sorts of microstructures that I just showed you, these materials don't have precipitate-free zones. And that's a big, big plus for aluminium alloys. And I think I'm just going to take a few moments to talk about some new things in the context of precipitate-free zones, because this, for anybody who works on damage properties, that you'll know that precipitate-free zones can really be a very big problem for us, basically because they represent regions of mechanical contrast with other parts of the microstructure. And so one of the things we wanted to see is, can we use dynamic precipitation to repair the precipitate-free zones that might exist in normal, conventionally aged aluminium alloys? And to give you an example, here are some precipitate-free zones in the sorts of alloys that we've been using. So you can see up here, this is 2024, so an aluminium copper magnesium alloy that's been peak aged, 6061 in the peak age state and 7050, and all of these materials contain precipitate zones anywhere from 70 to 120 nanometers in size. And so that's a reasonable size precipitate-free zone. Here's an aluminium copper example, and the precipitate-free zone can be about 200 nanometers in size. And so this is very important, because what you have here is a comparatively weak zone next to a hard grain interior. And that has some big effects on the mechanical response, particularly on the damage properties. And one of the particular damage properties, I'll just show you a few results for now, is the fatigue properties. And for those who work on aluminium alloys, despite us wanting to use aluminium alloys for lightweighting applications in transport, actually aluminium alloys, especially the precipitate strengthened ones, they have really terrible high cycle fatigue properties. It's quite remarkable, actually. If you take something like a steel over a very, very large range of steel grades and strengths, the fatigue ratio for steel, let's say the fatigue strength divided by the UTS, is about 0.5. For aluminium alloys, the same ratio is about 0.3, and the correlation is not very good. And so for the same strength increment that you might get from manipulating the microstructure, your return on investment in terms of improved high cycle fatigue performance is much worse for aluminium alloys. And that's a bit of a problem when we want to use aluminium in transport applications. And to show you how important precipitate-free zones are for this, I show you here two optical profilometry images. So these are optical profilometry images of the surface roughness of a fatigue sample. In this case, it's aluminium copper. And your image on the left is before the material has been subject to high cycle fatigue. And so we've performed fully reversed high cycle fatigue on smooth samples here. This is aluminium copper in the peak aged state, so it's got precipitates, and actually along here there's a grain boundary. Now, if we cycle this material at an alternating stress of about 125 megapascals for about 25,000 cycles, in fact, this is what you see develop at the grain boundary. And so these are identical regions, and you can see from these little points here. You see them on both cases. And so what that represents there is a massive localization of plasticity in the precipitate-free zone. And what happens in aluminium alloys is this plasticity localizes. It eventually leads to the formation of a crack, and then the material starts to break. Now, in fatigue, and I know certainly at Imperial you have many experts working in fatigue, there's many processes, they all matter. You have cyclic plasticity, you have the development of a localization of plasticity, fatigue crack initiation, the formation of a critically sized crack followed by fatigue crack growth and final failure. All of the stages matter, but for different types of fatigue loading, one or the other can dominate the lifetime. And in high cycle fatigue, it's really the time required to generate a critically sized crack that dominates most of the lifetime, certainly in lab-sized materials. And so these processes of fatigue, of plasticity localization in the precipitate-free zones is a really important process, and actually we'd like to delay it. Now, precipitate-free zones, in fact, they're not all the same. They don't have precipitates, but the reason for not having precipitates comes in multiple flavors. In fact, when we first start aging a material, let's say for a short amount of time, precipitate-free zones are there almost as soon as precipitation starts. But initially, the reason that they are depleted is because they are vacancy depleted. The excess vacancies annihilate at the grain boundaries, and in these regions then there's not enough vacancies to have enough mass transfer to make the precipitates. So you might have precipitates out here in the bulk, you've got no precipitates here, but you do have solute left in the boundaries. Now, as you age for longer times, slowly that solute will get to the boundary, it'll form grain boundary precipitates, and then you have a solute depleted precipitate-free zone as well. Now, this is very interesting because if you start with this type of precipitate-free zone, and you begin to cycle the material, the plasticity is first going to localize in the precipitate-free zones. And if you can control this well, then in principle, you can drive dynamic precipitation in the precipitate-free zones and strengthen these regions to remove the mechanical contrast between the grain interior and the precipitate-free zone. And so this was the idea. Now, if this is correct, you would expect that you probably can have better high cycle fatigue performance in the underage materials compared to the peak age materials, even though this material would be macroscopically weaker. And so indeed, we've done exactly those sorts of tests on all sorts of materials. I show you here, these are classic SN curves. They're generated fully reversed axial loading on smooth samples. And the blue and the red curves represent the peak age state and the underage state. So there's the SN curve for the peak age state for 2024, and the red curve is for the underage state. So we'll come back to the green curve in a moment. So consistently, the underaged material has better high cycle fatigue performance than the peak aged material. So the weaker material performs better in high cycle fatigue than the stronger peak age state. And so this is exactly the opposite of what would be expected, for example, from people working in the steel, where we see this very strong correlation between the fatigue strength and the UTS. And so if we look at the microstructures, in fact, we can indeed see that within the precipitate-free zones for each of these alloys after fatigue, we have dynamic precipitation. And we also see this very clearly in analysis of optical profilometry of the surface. And so what we have here is a series of optical profilometry across grain boundaries in peak age states, 2024, 60, 61 and 70, 50 after cycling. And we have this bigger localization of plasticity, 100 to 200 nanometers in size after the sorts of numbers of cycles here. And this is the equivalent case for the underaged material. Same number of cycles, and we typically now have the magnitudes of the plasticity localization is 50 nanometers or less. So there's a huge change in the distribution of plasticity. It's much more uniform in the underage state, And part of the reason is that we're able to remove that contrast between the grain interiors and the precipitate-free zones by dynamic precipitation. So it's sort of like a form of self-healing. Now, that is just looking at the underaged material comparing to the peak aged. Now that we have a proof of concept, you can take this one step forward. You can even design a particular training scheme for your materials before you subject them to normal high cycle fatigue to train them to repair the precipitate-free zones. And so that's what we've done for our materials. We can design particular training schemes. It might look something like this, and then you go down and apply your normal high cycle fatigue. And what it does is it generates dynamic precipitation. We have to control, we design this very carefully to specifically get dynamic precipitation in the precipitate-free zones to try to minimize the strength contrast between the grain interior and the grain boundary regions, and then do a normal high cycle fatigue test. And that's what's shown on the green curves here, and you have even further improvement in the high cycle fatigue performance. And so if we look at something like a 7000 series alloy, which is used in the aerospace applications, we're talking about something like an improvement in the high cycle fatigue performance, let's say lifetime, of maybe a factor of 30 or 40 compared to the traditional peak age state. And so this is a very interesting area, and it came about from our interest in coupling plasticity and precipitation. So I know I've gone on. I think what I'll do here is I'll stop. You can read these summaries, and look, I really appreciate you listening to me. I'll do whatever I can to answer your questions. I hope there was something interesting in there for you. So thank you very much.